Okay, today we're going to look at Chapter 6 of this booklet on second and higher order ODEs. So we're going to start with second order linear equations, and I'm going to show you why we should call them linear equations even though they're second order. So let's give a definition first. A second order ODE is said to be linear if we can write it as second derivative of y with respect to t plus a function of t times the derivative of y with respect to t plus another function of t times y is equal to a function of t. So that's a linear second order ODE. If we have the right hand side being equal to 0, then we call it homogeneous. Alright, so let's go ahead and make sense of the term linear here. So let's let z be equal to y dash. Then equation 16 up here becomes y dash is equal to z, just as we let that be up here. And then differentiating z with respect to t, we get z dash is y double dash, but y double dash can be expressed as taking all of this over to the right hand side, so that we have y double dash is equal to minus pt y dash minus yt y plus rt. Okay, so this line here is just a rearrangement of equation 16, where z dash is y double dash. So now we've set out two equations where we've got derivatives on the left and functions of t and y of t on the right hand side. So we can write that as a matrix equation where we let y uppercase y dash of t be lowercase y dash with z dash underneath that. And then on the right of these two simultaneous equations, we can translate that into a matrix equation where uppercase y of t is lowercase y of t followed by z of t. So the top line, if I multiply that out, I get 0 times lowercase y of t plus 1 times z of t, which is just the top equation here, and then plus 0. Now the second equation is minus q of t multiplied by lowercase y of t, and then minus p of t multiplied by z of t. So that's this little part of it, and then we add on r of t. Okay, so this looks like a linear equation because we've got a matrix equation. And you could even set out, let uppercase A be this square matrix here on the left of y of t, and b equal to 0 r of t. And then we have equation 18, which is really equation 16, becomes uppercase y dash of t is equal to a times y of t plus b. Okay, so clearly we see a linear equation there, much as we would with a first order linear equation. All right, so that's why we call this second order equation, equation 16, a linear equation. Now we can go further and show you how to relate the solution of this equation to matrix methods, eigenvalues, and eigenvectors. So we suppose now that p and q are constants, then the eigenvalues of the matrix A are given by the determinant of A minus lambda I equals 0. Okay, now that gives a quadratic equation there if you go ahead and take the eigenvalues. Now you might need to go ahead and read or reread Math 201 notes on eigenvalues and eigenvectors briefly to make sense of that. Okay, so taking the eigenvalues of that matrix A in the case that p and q are constant and simplifying that, so this is how we would calculate this. Here we have the matrix A, and then here's minus lambda I Okay, we add those two together, and we're taking the determinant of minus lambda 1 minus q and then minus p minus lambda. So that gives us a quadratic equation. Remember, we multiply the diagonal elements and take away the product of the off-diagonal elements. And so from that we get lambda squared plus p lambda plus q, right, which is equal to 0 because we were taking the determinant of this matrix equal to 0. Okay, so we call this equation the characteristic equation, but notice that when you're solving for lambda, you don't have to go through all of this process. You can just look at the coefficients and straight away write down the characteristic equation of equation 16. Because you look at this and it looks very much like equation 16 there. Right, you replace the second derivative with a lambda squared, the first derivative with a lambda, and since we're looking at the homogeneous case there, right, it looks very much like equation 20, or the characteristic equation. So what we want to do next, in order to find these eigenvalues, we need to solve or factorize this equation. You choose, depending on what's easier, solving using the quadratic formula or factorization if you can see an easy factorization. But those eigenvalues are not always real numbers. Okay, let's have a look at proposition 6.1. Suppose that y1 and y2 are two linearly independent solutions to the homogeneous ODE, y double dash plus p of t y dash plus q of t y equals 0. And by linearly independent, we mean that y1 is not a constant times y2. The claim here is that the general solution is given by a linear combination of y1 and y2, meaning the general solution is c1 y1 plus c2 y2, where c1 and c2 are constants. So let's have a look at why this might be. So assume that we have two solutions, y1 and y2, so then they would satisfy this equation up here. Both of them would. Okay, now c1 times the first equation plus c2 times the second equation gives us this line at the very bottom. Right, we just multiply those constants and add, and we have 0 on the right hand side. Now we can put the second derivatives together, the first derivatives together, and the single y1 and y2 together, and that looks like what we have here on the top right. And in fact, after we put the second derivatives together, we can say, well, the sum of those two second derivatives is actually the second derivative of the sum. So c1 y1 plus c2 y2 differentiated 2 times would be c1 y1 double dash plus c2 y2 double dash, right? Which is what we would have if we just shifted over that c2y double dash. Okay, likewise with the first derivative, we can take the sum and then differentiate. Okay, now let's call this c1 y1 plus c2 y2. Let's call that y3. Okay, so when we do that, we have y3 satisfies the same second order differential equation, right? So that we see why this is true. So if we have two linearly independent solutions to the homogeneous ODE, then the general solution is the linear combination of the two. All right, let's move on to section 6.2. Second order linear homogeneous equations with constant coefficients. A second order homogeneous ODE with constant coefficients, let's assume A is non-zero and B and C are constants, is an equation of the form AY double dash plus BY dash plus CY equals 0. To see the form of general solution, we first try y equal to e to the lambda times t, where lambda satisfies the characteristic equation 20 that we got from eigenvalues, with p being equal to b over a. So we're just taking equation 21 and dividing throughout by a, so that we have y double dash plus a constant times y dash plus a constant times y equals 0. And let's just call those P and Q, just so that it matches equation 16 with the right hand side being 0, because we're looking at homogeneous equations. Okay, now we're trying y equal to e to the lambda times t and subbing it into the ODE and seeing what we get. So we're differentiating twice e to the lambda t. Now what that does is, because the derivative of e to the lambda t requires the chain rule, which means that you need to pull down a lambda, and then you differentiate again, so you have to pull down another lambda. And so for that second derivative, we end up with a lambda squared e to the lambda t. Okay, likewise with this second part of it, we have b plus the derivative of e to the lambda t is b lambda e to the lambda t, and then c e to the lambda t is of course c e to the lambda t. I can see a little typo there, which I better write down. On page 53 or 54. I fixed all the earlier typos, but again, I'll upload that later. Okay, so where were we? Yep, that should be up in the exponent. Okay, so now we can factorize out the e to the lambda t outside of the expression, and then also factorize out an a, and so we get lambda squared plus p lambda plus q outside of a e to the lambda t. Now you see the characteristic equation there on the left, or at least the left-hand side of that, right? Which is meant to be equal to 0. So what we have is that, yes, we see indeed e to the lambda t is a solution to equation 21. And there's another typo up here, right? The t should be up in the exponent. Okay. So since a e to the lambda t is non-zero, we must have lambda squared plus p lambda plus q equals 0. So it follows that y equals e to the lambda times t, with t up in the exponent, is a solution to the ODE, where lambda is an eigenvalue of the matrix A, or a root of the characteristic equation, right? Because of course you don't have to take eigenvalues every time, you just set up the characteristic equation and you solve that. So for the general solution, we use proposition 6.1, which is on the left here, which we just looked at. When the characteristic equation has two distinct roots, the general solution will be given by a linear combination of the two. So in other words, c1 e to the lambda 1t plus c2 e to the lambda 2t, where lambda 1 and lambda 2 are non-equal and roots of the characteristic equation. However, when lambda 1 and lambda 2 are equal, we have the general solution being c1 e to the lambda 1t plus c2t e to the lambda 2t. But we know that the roots of the characteristic equation are not always real numbers. So let's have a look at this, because it's still true in the case that they're not real numbers. However, we go and interpret those somewhat differently. Okay, so suppose our lambda is equal to alpha plus beta I, where I is the square root of -1. So we have a real part alpha and an imaginary part beta. Alpha and beta are both real numbers. Okay, now let's use Euler's identity. E to the theta I is cos theta plus I sine theta. Suppose we have lambda 1 is alpha plus beta I, and lambda 2 is alpha minus beta I. Now, complex roots of equations by the fundamental theorem of algebra, they always come in pairs that are complex conjugates. Okay, so if I have alpha plus beta I as one root of a polynomial, then alpha minus beta I is another root of the polynomial. Like I said, they always come in pairs. So we can assume this is the general case here. All right, so then c1 e to the lambda 1t plus c2 e to the lambda 2t is C1 e to the alpha plus beta I all outside of t, plus C1 e to the alpha minus beta I all outside of t. And now we want to simplify this a little bit, right? Because an exponent rule says we can break this up as a product. So we've got C1 e to the alpha t times e to the alpha beta ti. And then likewise something similar here. Now we can see that e to the alpha t is common in both, so we can factorize that out the front. And then finally we can use equation 24, Euler's identity there, to simplify this. So we have e to the beta ti is cos beta t plus I sine beta t. And then in front of that we've got C1. Likewise for the second part, e to the minus beta I t is cos of minus beta t plus I sine of minus beta t, and we have a C2 in front of those. Okay, so next we want to collect the sine and the cos together and then put the constants nicely collected in front. So we still have e to the alpha t outside of the whole thing, but the coefficient of cos of beta t is C1 plus C2. So we take this and put it next to the other cos. Now cos of minus beta t is the same as cos of beta t. We say that cos is an even function. However, sine is an odd function, so sine of minus beta t is minus sine of beta t. So that's why we have a difference as the coefficient there of sine of beta t. Okay, and we still have the letter I there, which is, we have an imaginary number. So this is not real. However, what we can do, amazingly, is let some new constants a and b be C1 plus C2 and C1 minus C2I. Okay, and then we see then that our general solution to the ODE in the case that our eigenvalues are not real is e to the alpha t outside of a cos beta t plus b sine beta t. And amazingly, it turns out that in real-world applications in which you have complex eigenvalues, you end up with real values of a and b. Okay, so complex numbers are a part of calculating a solution to a real engineering, physics, chemistry problem or economics problem. So they're no more, fake than other numbers. They're I'm thinking of the word real, right? They're no less real is what I'm trying to say. Okay, let's have a look at our next proposition here, which collects all of those results together. So we've already seen why that's true, more or less. Proposition 6.2, the ODE a y double dash plus by dash plus c y equals 0, where a is non-zero and b and c are constants. Let's let delta equal b squared minus 4ac. Now this is the discriminant of the characteristic equation. The number inside the square root in the quadratic formula. Okay, so if delta is positive, then we have the general solution a e to the lambda 1t plus b e to the lambda 2t. In that case, lambda 1 and lambda 2 will both be distinct real numbers. So if the number inside your square root in the quadratic formula is 0, so if delta equals 0, then we have y equals a plus bt all outside of e to the lambda t. And finally, if delta is negative, that's the case where we have a negative inside our square root, and so we have two complex conjugate roots of our quadratic equation, which is the characteristic equation. So they're complex, and so we go for the form down here on the left, which is expressed right here. So e to the alpha t outside of a cos of beta t plus b sine of beta t, where alpha is the real part of lambda and beta is the imaginary part of lambda. Okay, and lambda are the roots of the characteristic equation there. All right, so let's reflect again on the fundamental theorem of algebra here. in the case that delta is 0, the quadratic formula gives us repeated roots. And by that, because the fundamental theorem of algebra says that since we have a degree 2 polynomial, we expect 2 roots, but they can be repeated. So that is this case, they're repeated. We've got lambda is equal to minus b on 2a, but it's there twice when you're viewing this in terms of factorization. So we have y1 equals e to the minus b over 2at is one solution to the ODE. To find the other solution, we let y2 be equal to u times y1, and then we substitute into the ODE. Okay, so we have a times the second derivative of uy1 plus b times the first derivative of uy1 plus c times uy1. And now we've got to use the product rule and then rearrange. So I'll let you go through the details of that. But after we do that, we get a u double dash plus 2a lambda plus b u dash, then plus the left-hand side of the characteristic equation times u, all outside of e to the minus b over 2a all times t. Now, because of the characteristic equation, we've got this next to u here is equal to 0, and lambda is equal to minus b on 2a. So both of these two terms are 0 there. So the equation just becomes u double dash is equal to 0. Okay, and so integration gives us that u is equal to a plus bt, which completes the verification of proposition 6.2. That's the case 2 here, that we have y equal to a plus bt all outside of e to the lambda t. All right, now let's move on to example 6.1, which is our first example here. It's a very simple equation. To solve the second order ODE, y double dash plus 2y dash plus y is equal to 0, we first write the characteristic equation, okay, and now we want to solve this, but it's easy to do that by factorization. We see that we've got a repeated root there, lambda is equal to minus 1. And that's the case where delta is equal to 0. Okay, so our general solution is in what we have here in case 2, y is equal to a plus bt all outside of e to the lambda t, but lambda here is minus 1, so that's e to the minus t. All right, so now let's look at some applications. So the first one here comes from physics, where we've got a spring there in figure 15 attached to a mass at the bottom and, say, a ceiling at the top. So this is a spring mass system. The question here says, use the laws of physics to model the motion of the mass at the end of the spring. We let y of t be the vertical displacement of the mass at time t from equilibrium position hanging under gravity. So really we've got two equilibriums here. We've got the equilibrium of the spring itself when this spring is horizontal, right? Because the spring will want to stay naturally in one position. And then we have another equilibrium that is due to gravity, because it gets pulled down by gravity to find a new equilibrium when it's vertical. So the restoring force towards equilibrium is given by Hooke's law. F subscript r is minus kd, where d is the displacement from equilibrium, and k is the spring constant particular to that spring. This displacement is given by d is equal to s plus y of t, where s is the difference in equilibria of the spring horizontally and vertically under gravity. Remember, we said we have two equilibriums, one when it's horizontal and then another when it's vertical, because it gets pulled down more to a new equilibrium. So the force due to gravity is F equals mass times acceleration due to gravity, or mg, where let's assume g is 9.8 meters per second squared. So the sum of the forces on the mass is F equals F subscript r plus F subscript g, which is minus k outside of s plus y, and then plus mg. Now Newton's law of motion says F equals ma, so on the left-hand side we have ma, but a is a second derivative of that displacement with respect to time. So my double dash is equal to what we have here, because those forces are in equilibrium. Okay, so now we can go ahead and divide throughout by m. And use the fact that initially we have f equal to 0 when y is 0, so that gives us minus k. S plus 0 plus mg is 0. In other words, ks is equal to mg. So this greatly simplifies, right? So we have my double dash plus ky equals 0. So m is non-zero, and we can divide by that, and so we have y double dash plus k over m, y is equal to 0. And now we say, let's let k over m be omega squared. And why omega squared, you might ask, rather than just omega? Well, because it'll simplify the form of the solution a little bit for us. So we let omega be the square root of k over m. In other words, omega squared is k over m. So that's a second order linear homogeneous ODE with constant coefficients. So the characteristic equation here is lambda squared plus omega squared is equal to 0. Okay, and so solving this is easy. We take the omega squared over to the right-hand side, take square roots, and so we get lambda is equal to plus or minus omega I. Again, where I is the square root of minus 1. So using proposition 6.2 here, where we've set all the cases out, we have the general solution. Now in our case, alpha is equal to 0. We don't have any real part. We just have an imaginary part, beta. So it's a little bit easier here. Okay, so beta is omega. So we have roots. Lambda 1 is omega I, and lambda 2 is minus omega I. Proposition 6.1 gives us that the general solution is a cos of omega t plus b sine of omega t. All right, now we can simplify this a little bit more using the angle addition formula for cos. Cos of a plus b is equal to cos of a times cos of b minus sine of a times sine of b. And so we can write the sum of these two cos and sine functions as c cos of omega t minus some letter phi. Okay, so we're just setting out that c times cos of minus phi, the Greek letter phi, is our constant a, and c sine of minus phi is our constant b. So that we can say that this is looking a little bit simpler in our general formula. Y of t is c cos of omega t minus phi. Okay, so that's what we have here, where again omega is the square root of k over m. Now if we make this special and say let's let m be 2 kilograms, let's assume that the spring constant is 6 newtons per meter. Now if the spring is pulled 1 meter from equilibrium and the initial speed is negative 1 meters per second, so that's in a particular direction, then we have omega is the square root of 3. We have y of 0 is 1 and y dash of 0 is minus 1. So we now have an initial value problem that's second order. We know our general solution here at c cos of root 3t minus phi. And we have t equals 0 when y is 0. And I can see I'm missing a word there, page 59. Okay, and so that gives us c cos of phi is equal to 1. So it gives us a way to find these values here. So differentiating, we have y dash is equal to minus root 3c sine of root 3 t minus phi. And since y dash of 0 is minus 1, we then get root 3 c sine of phi is minus 1. Subbing in 0 for t and minus 1 for y there. All right, now we've got equation 26 and equation 27 established from those initial conditions. So we want to find c and phi to get our particular solution here. But to do that, we should divide equation 27 by equation 26 so that the c vanishes. And when we do that, we get root 3 tan of phi is minus 1. So now we've got an equation just in the letter phi that we can solve for phi. So we've got two solutions to this equation. So between 0 and 2 pi radians, phi is equal to pi minus pi on 6, which is 5 pi on 6, or we've got phi is equal to 2 pi minus pi on 6, which is 11 pi on 6. And so that gives us a solution c and phi equal to minus 2 over root 3, 5 pi on 6, or 2 over root 3, it's positive 2 over root 3, 11 pi on 6. However, these two give you the same solution, and you can just plot it to check that that those are the same. Okay, so that gives us our solution to that equation. Now, it's not entirely realistic because we've totally neglected air resistance. So in this case, if we include air resistance in the equation, we have a damping force that acts in the opposite direction to the speed, right? So if you're moving through the fluid being the air, the resistance is the opposite direction. So that's why we have a damping force that's minus some beta times the speed here, y dash. Okay, so if we let beta on m be equal to 2 rho, then the resulting ODE is of the form y double dash plus 2 rho y dash plus omega squared is equal to 0. Hang on, I think that should be omega squared times y. So it's page 60, omega squared y equals 0. It's amazing when you go through this again that you find a number of typos that you didn't see when you wrote this thing. Okay. So the general solution for this is given by a e to the minus rho t cos of the square root of rho squared minus, or sorry, omega squared minus rho squared all times t and then minus phi. So there's a component of exponential decay here, right, which is in the front, which makes this spring tend back to equilibrium. Remember, this is the case where you have air resistance, so you have an air resistance force on it. So as you might expect if you've ever pulled a spring, air resistance is the thing, you know, and probably some resistance within the spring that makes this spring go slower and slower and slower back to its equilibrium solution. Right, and if I were to graph this, so above, if you look at the graph in figure 16, we've just got a cos wave there, right? However, if we include air resistance, you would see a cos wave that gets smaller and smaller in amplitude over time and tends back to the equilibrium solution. Okay, so now let's have a look at second order non-homogeneous equations. So where we don't have a 0 on the right hand side. Let's still assume that P and Q are constants and look at how we might solve such an equation. So step 1 would be to solve the situation as when it were equal to 0. So in other words, solve the homogeneous equation and call that solution y subscript h. And then what you do is you guess a particular solution y subscript p that is based on the way that r of t looks as a function. Like, what kind of function is it? And you want to match your guess to be something that you know is going to work out. Okay, and that comes with either, making a list of how things work out or just by experience. Okay, and then finally you write the general solution as the sum of the homogeneous solution plus the particular solution that came from your guess. So now let's have a look at an example with a pendulum, a forced pendulum. So consider a pendulum oscillating under gravity in the absence of air resistance. So we have F is equal to ma, so that's m times the second derivative of r theta. So remember, r theta is the arc length of your circle there. So this is equal to minus mass times gravity sine of the angle theta. So we can write that, dividing the equation throughout by m, we can write that as theta double dash, and dividing it throughout by r. Theta double dash plus g over the radius r sine theta equals 0. Okay, so that's a nonlinear second order ODE. It's nonlinear because this is nonlinear in theta. Here, sine theta is a nonlinear function in theta. But fortunately for small theta, the Taylor series gives us an approximation of sine theta, saying it's approximately equal to theta. And so we can simplify this ODE when theta is small, because remember the Taylor series is accurate when the thing you're taking the Taylor series about, in this case 0, is close to the actual theta, right? So it's just how the Taylor series works. And I imagine this will have been gone over in the numerical analysis course that's offered by USC, but I don't know for sure. Okay, so we approximate this equation with theta double dash plus g over r theta equals 0. Now we want to include air resistance in the calculation, so we then have a forcing function which we'll replace the 0 on the right hand side with, say 2t plus 1, for example. Okay, so that gives us a new equation that looks something like this. And then now assume that we've got 9.8 for gravity. Suppose we've got 4.9 meters as the length of our pendulum stick, and p equals 1. Suppose initially we've got an initial angle of pi on 4 radians, and a speed of that angle initially equal to minus 1. So that gives us an initial value problem to solve. We've got a second order ODE. We've got a forcing function on the right. We've got initial values. So let's begin solving this by solving the homogeneous equation. So we set out the homogeneous equation, and then from there we write down the characteristic equation. Now we've got to solve this characteristic equation. So in this case, the factorization does not look easy, so we go for the quadratic formula, which is right here, but the inside of the square root is negative. So we have 1 minus 8, which is minus 7. So we write that as root 7i there. Okay, so lambda is equal to minus a half plus or minus a half root 7i. So our real part is minus a half. Our imaginary part is a half root 7. And so our general solution from proposition 6.2 was it? Way back here? Yes, proposition 6.2. That's the third case. We've got e to the real part times t, so e to the minus a half t, all outside of a cos of beta t plus b sine of beta t. But beta is just a half root 7. So for a particular solution, so now this is the general solution to the homogeneous case. So we just hold on to that for now. Now we're looking for a particular solution. So we might set out the same form that we have on the right hand side for r of t. So we'll say let it be a t squared plus bt plus c. In other words, a polynomial. We put a high enough degree to accommodate differentiating that twice. Okay, so now we want to differentiate theta subscript p 2 times and sub it back into our ODE. So the first derivative there is 2at plus b, and then differentiating that again with respect to t gives us just 2a. So now we take these two, we sub it back into the ODE, and we compare. So subbing in 2at plus b, that goes in where theta dash is, but 2a is the second derivative, so we have 2a t squared plus 2at plus 2bt, right? All of this is equal to 2t plus 1. Okay, so we solve that because we need the coefficients of these things to match. We've got a is 0, b is 1, and c is 0. So that just gives us that theta subscript p is t. It's very simple in this case. Okay, so we've got our homogeneous solution and our particular solution that we guessed. Now we just add those together to find the general solution to the non-homogeneous equation there. And that looks like this at the top of the left here. Okay, so next what we do is we use our initial values to find the value of a and b. All right, so we just sub those in. There's a lot of calculation to do, but we can simplify and then solve for a and b. So we get a value of b, and then we can use that to get our value of a. So that gives us the solution here, which looks a little bit unwieldy. But the thing to notice here is even though the demonstration of that proposition 6.2 required complex numbers, you notice that your constants are not complex numbers, right? Which is a bit amazing because this is a physical problem that required complex numbers in, the production of the solution. But you see that your constants there are not complex numbers, they're real numbers. All right, so finally let's move on to nth order homogeneous equations with constant coefficients. Now, these equations can be solved in much the same way. And the reason why is because you can formulate this as an n by n matrix equation and see that it's still linear, and you proceed to solve that using eigenvalues. Okay, so that's why these solutions look very similar. So let's have a look at example 6.4. Solve the fourth order ODE y fourth derivative. Now you can see the notation here. We stop using dashes and just put a superscript 4 with a round bracket around it for the fourth derivative because it's more concise, right? So y superscript 4 of t minus y superscript 2, so that would be y double dash of t minus 6y is equal to 0. So we begin with characteristic equation. Now it's a fourth power characteristic equation. Lambda to the fourth minus lambda squared minus 6 is equal to 0. So this one is easy to factorize over quadratics. So we can factorize that as lambda squared minus 3 times lambda squared plus 2 equals 0. And then the left-hand factor is easy enough to factorize again in terms of linear polynomials. So we have lambda plus root 3 times lambda minus root 3. And similarly, you can factorize lambda squared plus 2 provided you use complex numbers to do so. So you have lambda plus root 2i minus times lambda minus root 2i, and all of these multiply together to give 0. Okay, so that gives us 4 roots in agreement with the fundamental theorem of algebra, because this characteristic polynomial is of degree 4, so we expect 4 roots here. So those roots are lambda 1 is minus root 3, lambda 2 is root 3, lambda 3 is minus root 2i, and lambda 4 is root 2i. And then we just write down the characteristic, we write down the general solution just using the same technique that we had in proposition 6.2. We've got a1 e to the lambda 1 t plus a2 e to the lambda 2 t, and then since these are complex and not real, we have A3 cos of beta t plus A4 cos, that should be sine of beta t, right? So another typo there on page 64. Okay, and I think that's all for this half of the booklet. So I've got to go back and write some more notes, and I'll get back and make another video. So see you next time. Thanks.